Welcome again for a video about Apache Tuweni. Today we're going to talk about something a little different. We're going to talk about the Ethereum Virtual Machine. So this is Apache Tuweni. We're a project. We're doing all sorts of things with Ethereum, but also other distributed systems like Secure Scuttlebutt. One of the big things that folks, when they look at Ethereum, really like is to look at the Ethereum Virtual Machine. And it's a little daunting because the Ethereum Virtual Machine is defined in the yellow paper, which is very much like a scientific paper. And the goal of this video is going to show you how we implemented part of it. I'll explain exactly what that means and what's the future of that code and how you can help. And we'll also explain how this is done in a way that makes it super easy for anyone to understand what's going on, how to make it better, how to compare it with other implementations as well. So first off, we're going to start in the EVM module. It's part of our GitHub repository here. The EVM module is relatively recent. We added it last year. The point first was to start with a implementation of the EVM based on EVMC. And then as Bintray was being removed, we found out it was no longer possible for us to have EVMC Java libraries on Bintray. So kind of stuck between a rock and a hard place. I decided, okay, you know what? I'm going to try. Well, how hard could it be to implement your own EVM, right? So this is not the whole thing, but there's a good chunk of the EVM here, and I'm going to explain all the components to you in this description. So you want to start in this Ethereum Virtual Machine.kt file. It's interesting in IntelliJ you see .kt. You know why? It's because there's multiple classes defining this. Right? When there's only one class in IntelliJ, it will remove the file extension. But with Kotlin, you can actually have multiple classes defining one file, and Kotlin will be just fine with it. Right? So because of that, you may see less files in this particular library, but there's actually quite a few things going on at the same time. The first thing you want to start with is this Ethereum Virtual Machine class. Right? It's taking a few things as a part of its constructor. The first one is a blockchain repository, which actually hosts all the components of your blockchain, from the point of your transactions, your blocks, your current head, even data about your account, data from the past. Everything is stored in there. That should be its own thing by itself. Rest assured, it's very much access to what you would call a database in Geth, for example, everything in level DB, right? We have a EVM VM factory, which is something that creates EVM VMs for us. And as you can see, we're not just having one instance of a VM. You can actually create them on demand. And that's interesting because you can actually have a way to then inject your own VM over time. When you start, you can create, you call the EVM VM factory function, you get a VM for it, you set some options on it. When you stop, you would close that. And when you execute, you're passing a whole array of parameters in, which are going to be translated into an object that is being then passed into the execute internal function that calls to the VM. Right? So here, right? So a whole bunch of context being passed in to this mysterious function that it then executes. Now let's go back. What are those parameters and what do they do? Those parameters are well known in the Ethereum world. Like, they come from the context of the execution of a particular transaction. So you can imagine all things which are sender, destination, the value of the money being exchanged, right, in ETH, the code that is part of the transaction, if it's a create, if we're deploying a contract, the input data. So if you're going to call a contract, you would want to have parameters passed in. That's how you do it. How much gas you're going to pass in, what's the gas price at the time, the coin base. This is the current coin base of the environment, so who is mining this block, right? The number, this current block number, that's super important for some contracts that want to operate differently based on the block number, which is kind of a hard one. The current timestamp, that's a timestamp of your block, difficulty, gas limit, what type of call are we talking about. So this is actually an enumeration. You can have calls, they get calls, you can do create to. right? Stop things. So the VM itself is actually running over here. And when you create a VM, what's really interesting is there's a couple of things happening. First, you register everything's going to happen on the VM in terms of opcodes and things like that, right? So there's an opcode registry create here that's creating this registry that now lives inside the VM. There is also, as part of the execution, so more in a transient way, a little bit of a set of things, that objects that are going to participate in the execution. So now we're down to the execution of the code. We passed in our parameters. We registered some steps, some opcodes. I'm going to go over that in very big detail in a second, but you were just calling this EVM and it's ready to go. So the first thing it's going to do is create a stack. The stack is the execution stack of the EVM. You're going to create a gas manager, which is going to manage your how much gas you're expending as part of this. So if you're spending too much, we want to stop the execution. We're going to talk a little bit about the memory that is attached to the EVM itself, to the execution, and we're going to then execute, right? So for the execution path that we have is we're going to just keep going across until we're done with the execution. And we're going to, if we have trace enable, we'll be able to print out the stack, understand a little bit more what's going on. We're going to get from the registry the right opcode. So we look at the first byte. From that, we can actually define which opcode we should call, right? If there's no opcode for that byte, then we'll stop here. We'll say invalid instruction, please exit gracefully. If now we can have the current opcode byte, we're going to increment our walk by 1 byte, right? So we're now past this opcode byte, and then we execute, right? Using the opcode execute function. So each opcode executes on its own, and you can see that there's a result, right? So the result itself has a couple fields on it. One is that it's got a status. Well, if it's not null, then maybe we need to pay attention where it's at. If it's a successful status and we don't have any gas left, then we need to exit right away because we're out of gas. Otherwise, well, we made it, folks. We're out of this and we're done. So this is important because some opcodes can actually tell you terminate the execution now, even though you haven't walked the whole tree of bytes, right? If there's still some stuff you could consume, but you have to stop now. Other than that, if there is a new code position that's passed back as the opcode execution, then that becomes our current index. So this happens because we can jump inside the code. We can go back and forth, go from the end of the execution back to the beginning, and I'll show you there with some examples of that. If you don't have any gas left, and again, and we did not pass any results, well, we're out of gas. We have to stop. If we have too many things in the stack, meaning if we have stored too many things in the operands of our execution, we need to stop. We need to say we overflow. And finally, if we have any status that is not okay, and well, we need to say, okay, we have to stop now. So some opcodes can actually tell you halt execution and have exactly that error. And then, keep going. And if you come to the end of the execution and nothing has happened and you still have gas, well, I guess you're good to go. So let's mark it as good to go. Right? There's this little bit capability, which is a reminder of our EVMC compatibility, not yet implemented, right? So we don't do anything in terms of being able to say which capabilities we have in the VM. Now, those opcodes, well, they're being registered with opcode registry. So let's take a look at that. First off, what's an opcode? It's just a functional interface. In Kotlin, you don't have to have classes for everything. You can actually deploy things as part of a simple interface that takes a function, right? So as long as this function has this signature, you're good to go. What does that look like? Well, you have a gas manager, a host context, a stack, current message. the code that you're executing against, current index in that code, and the memory, right? And it returns a result, maybe, right? Because Kotlin allows you to say, this is actually meaningful in Kotlin where it says it's result or nothing, no. The Opcode registry here is being constructed here, but it could be very malleable, right? So some extensions from Enterprise or some of the chains may have different opinions about what registry should look like, what is the mapping to bytes. And we could see also, depending on the hard forks of Ethereum, we've seen new opcodes being registered or some of them being changed significantly. So for this one, we're kind of cheating because we're just going to do the Berlin hard fork. This is one of the big things that needs to happen for 20 to move forward now, is that we'll need to have a variation of those opcode executions for every one of the other hard forks. The good news is, yes, they're changing, they're different, they're mostly around the same model, right? So if anything, it's becoming more complex than before, right? So it would be possible to start bringing this type of things to others, and I would welcome any contribution on that. What we're passing in here is actually a function that's defined under the Berlin package, right? So I'm actually passing in something that I'm importing here at the top, right? And it's looking neat, but those imports are pretty gnarly, right? Now, also, what we're doing at the bottom, if I remember, we're also passing some functions that themselves are parameterizable with an int, right? So we didn't want to do push 1 to 32 one by one, so instead we're passing in a function that takes an argument and returns to you an opcode function with right integers. So, okay, that is our current opcodes for just Berlin. We're going to register that, and this is what we're going to execute with, right? Couple other things which are super important for the EVM. The first thing is there's no EVM without a stack, right? So you start with an empty stack, and you're going to add elements to the stack using the push or using the copy input data opcodes to add variables that you're going to execute against with the next opcode. So I'll show you an example, but the add opcode, for example, has 2 arguments which are members of the stack and outputs the result to the stack. If I remember correctly, the stack is a FIFO approach. Here we're cheating. We're cheating quite a bit because we're just going to create a big array of bytes where we're saying the max size is 10,025 items times 32, which is the default size of the word inside the EVM. And that gives you an array of bytes that you're going to play with, right? So we want to make sure we're not spending a whole lot of time copying bytes around, all that. We also don't want to allocate a bunch of memory. Even though we're in Java, there's actually a cost from the point of view of garbage collection. So what we're going to do is we're going to once and for all allocate this many bytes here using our mutable bytes class from the bytes library. And every time we are asked to pop or to get anything, we're going to give you the slice of things. The other thing we're not doing is when you pop, you don't actually invalidate what's in the stack, right? Because it would take time and performance away from the rest of our execution. So all we're doing is we're changing the loyal counter here that's participating in our size calculations, so we can know which one is current. But we are not going to nullify or empty our memory because that is just going to crush our performance. Right? So the only thing that's a little special here is that it can be overflowed, meaning that someone has put too many things in the stack compared to what is okay. And in that case, this method will return true. Okay, so that's a big one. The other one is memory. Memory is very important in the EVM because while the stack is great for things you want to do right now, you don't want to spend all your time playing with the stack. It's actually a pretty dangerous game because maybe you have something that doesn't really fit 32 bytes. Maybe you have something that you want to store across operations, right? So you don't want to have to keep it in the stack all the time. Memory allows you to do that, even though it's a little more expensive, if I remember correctly, from the gas prices. Someone from the internet can correct me on that. So you can write at any offset, right? And you can make all sorts of pronouncements about what you should be writing at. This being Java, in theory, memory is unlimited and however flowing and powerful. Reality is at some point we're going to say no, right? And how do we say no? We actually calculate the gas cost of you writing things to memory, and we make it prohibitively impossible for you to write a whole lot of things at a great offset or a whole lot of bytes without having to pay for it dearly. So there's a kind of a balance that we play here, where you would want to let people write to memory as much as they want, but we need to check first that you actually have what you need to do there, right? So if we don't bork or run the machine out of memory just because it decided it was a good time to write 8 gigabytes of bytes into memory. So kind of same idea here actually from the stack. The difference is now we're working with words, right, of 32 bytes. Everything is going to be in 32. If you have something that doesn't fit into 32-byte word, that's okay, because we're going to segment that across different words, right? When you ask for your memory back, we'll do the recombination of that together, right? So the memory data itself is contiguous because we don't have time to also play those games, right? So we're just going to store the data in memory as is, store it directly in here as part of our writes, and based off that we can recompute the new size based on what we want to do, right? So we can give you the allocated bytes, which is always going to be word size multiplied 32, right? Even though, let's say your memory is almost empty and just have 3 bytes in them, well, that's still a word. We're still going to allocate 32 bytes. You're still being charged for 32 bytes, right, in your gas cost. And then when you read stuff, well, we'll be able to then read that. We're very flexible, so if you ask to read more than is stored, for example, we'll make sure to only return what is actually stored without breaking the bank. Okay, now gas manager. Well, let's make it, hopefully that is going to be the clearest of all. You start with some gas, right? And at first you have a gas cost that is 0, right? Every time you do something, it adds to gas, right? So that gas cost becomes gas, and your gas cost is increased by how much gas you have, right? At some point, someone is going to ask you, do you have any gas left? Well, we can find out about that by doing a little bit of a compute here. But one of the things we want to do is to make sure that if you were to overflow because the gas cost is more than what is allowed, I think it's 2 power 64, then return 0, right? There's no gas left. None. It's just not possible. Otherwise, gas subtract gas cost, right? And if for any reason we want to know whether you have gas left or not, if you spent, if it's too high, meaning if it's negative, that means you don't have any gas left, pretty much. Okay, so trying to keep those classes as simple as possible, and you can see there's been some thought into trying to make them performant. Even though we do use rich objects for gas, for example, it's actually it's actually holding on to big integers in Java and all good stuff like that. So it's not a light object. We try to cache it, right? We try to cache the values using constants, for example. So small values already cached. We try not to allocate a whole lot of memory every time you run an EVM, because otherwise you're going to start seeing all sorts of issues. We will always be able to cache more as we go. But I think at some point we're reaching diminishing returns, and I think we've reached that already. Now, the real part of this show that is cool is all the opcodes. And people talk about opcodes quite a bit, right? So in the yellow paper, we talk about each and every one of them, and they're defined, they have a gas cost. Let's pick one that is really easy to understand. We're going to start with add. So the first thing we do is we add 3. And the L here is just because it's a long in Java. Please disregard. We're using a literal value here. Um, I'll explain in a second why we're doing this with a 3 and not passing in a constant. So, gas manager adds 3. Done. Now, pop from the stack 2 items, item 1 and item 2. No items being popped. We're not seeing them. Okay, we have to return right away. Stack underflow. Else, push in the stack item dot add item 2. Result, empty. Everything's fine. Move on to the next one. That's how hard it is to implement an opcode using this approach. This is purely functional. We're just passing in items and elements, and as you can see in Kotlin, you want to mark them as ignored using the underscore notation if they're not going to be used in the function. So this is a simple addition between 2 items in the stack. The addition itself is actually not easy at all. It's using those uint256 objects that we have in the back, and we are keeping those objects as a collection of integers, and then the addition itself is passing on all those items together and passing the increase between the integers as required. Okay, now we have add mod, not, we have all sorts of interesting things here. So we're passing all sorts of standard, very mild cost back to it. Equal, it's just when you're done, if it's equal, then pass back 1. If it's not equal, pass back 0, right? Same thing for L less than, S less than, or sign less than. So the sign less than is you're passing those 2 items, but then you're actually going to imply that there are signed values, meaning that it can be 2 complement values showing a negative sign. In that case, we pass them as big integers, and we're able to see if one is less than the other using this approach. There starts to be a bit more fun down the roads, wherein we do things like scrolling. So store, for example. Now we want to store something here. We want to store it in our storage on our blockchain, right? So we're going to have a key and a value that we're going to pop as stack arguments, right? Again, the stack is all about passing arguments to you and giving you results. Nothing? Okay, done. Stack underflow. The address is always the destination of the transaction itself, right? So the message destination is there. Based off that, we can now find out the storage of the account that we're going to play with. As part of this, we're going to figure out if you already created the slot on storage or not. If it's already created, then the cost is minimal, but if it's not, then you're going to have to pay a bit more. So let's take a look. Slot is warm, right? So this is a very simple host context function that goes and checks whether the storage has been used before or not. So we also get the current value, and then we're going to do a little bit of fun algorithmic. If our current value is equals to the value that is in storage, then that means our gas cost is a fixed constant value of 100. Other than that, well, in that case, we have to go and pick up the original value that is stored outside of our context, outside in the blockchain. If it's equal to the current value and the original value is 0, then our gas cost is going to be 20,000 minus 2,100. Otherwise, we're just going to do 5,000 minus 2,100. Else, gas value is 100. And that becomes, in Kotlin, a cool little function here that's passing back to cost. Add to that some additional logic here says if the slot is warm, then there's no cost. Otherwise, pay 2,100. And now you can add that to the gas manager. Okay. There's also a function, a provision here, which says if the remaining gas is less than 2,300, then you should exit right away. Right? And now we can actually set the storage to those things and return. I removed the gas refunds for now because I'm playing with this and I don't know how to make sense of that. So this is coming straight from Hyperledger Besu when we got started. Another one that'd be fun, and one that's really easy to stop, right? You just go away, or invalid, you just want things to just stop because they don't work. Return is interesting because it's different from stop, right? So now you want to return a value. You want to place an actual output from this. You can read that from the memory. So you're going to have two items, location and length, playing from the stack. And they're going to be creating a memory cost. We're going to find out whether we have to pay a whole lot for that. So we're going to see the memory size before and after reading this. And we're going to do pause subtract 3 from that. That's going to be added as a gas cost. Based on that, we read the memory, and now it becomes the output of the function. There's some other things that you can kind of are cool for this. These are all context functions. Like you want to see the origin of the transaction. That's going to be a message sender. No problem. We're going to left pad that value into 32 bytes because by default addresses are 20 bytes, and send that as a result, right? And so on and so forth. We have a whole lot more things like this that are coming down now. So all those opcodes, once implemented, start working right away. They make sense. You can use them to read the bytes, execute. Everything starts to just play along. So once you have that going, you can now execute them as part of the test. And let me show you those tests in a second. Why are we using constants? Well, there is a beauty, which it will bite, right? It will bite sometimes. There's beauty in being able to just look at a function like push, for example, and say, it's just adding 3 to gas. It's just doing those 5 things, right? So there's a whole lot of indirection you can add where you would pass all those as constants, things like that. The reality of it is it's not that required. It's not really helping. We can always optimize that later too. So completely imagine that we'll make it better, faster, really soon enough. But for now, this is fine, right? So it works as advertised. And the best thing is this implementation of EVM is really, really fast, right? Because it's all functional, there's practically no allocation of objects. You'll see that we can actually do a pretty good job at all passing all the reference tests. So those reference tests, well, kudos to Dimitri, to the Ethereum Foundation on that. I didn't have to come up with them. They've been maintained for years now. I mean, they've been really hard at work for any hard forks. You can see his work on the EF Discord. And the team there is managing all sorts of interesting tests that are creating an environment, telling us about the current transaction, tell us exactly what to execute. So this is the code we're going to execute, for example, with that gas, with that price, and gives us an idea of the state of the accounts in the world before and after, right? So ideally, when you do this execution, you would want to be able to compare those two things. Okay, so, well, let's go right to it. If I can get to it from here, I'll get from here. And what it does here is that we're reading all the JSON files that I just showed you, right? And as we find them, we prepare for them, and then we can execute each and every one of them to become a parameter to that function. Now, the test, we're going to, before it executes, recreate the state of the world before we get started, right? So we're going to create a blockchain repository and a Merkle partial tree for each of the accounts. They're going to store all the storage so we can recreate the keys and all that. And when we're done, we're going to be able to execute creating a Ethereum Virtual Machine and starting it. Now we execute this based on the JSON, so apologies for that. This is actually required by the JSON where we want to make sure that this is all present. And sometimes it might not be because some of the JSON tests don't have that. If there's no post state, that means that the test is not failed, right? Has not succeeded. Sorry. So we can actually make this assertion, right? The status code should never be a success. Then, based on past tests and behaviors we've seen, we know that some of those tests would expect to have a bad jump destination. Some other tests have a stack underflow. Some others would run out of gas. At least one of them has a stack overflow. And, well, if you don't see that, then we have a to-do here. And to-do in Kotlin actually throws an exception when it gets to it, right? It's kind of a nice little notation that does everything at once, right? So now we can actually, if we see any test that comes up and is not satisfied by any of those conditions, we can go and fix them as we go along. Otherwise, well, better get success. Now we have a post state, so we can actually check for each and every one of the accounts that all the account keys and values match what we expected, that the balance of the accounts match what we expected, and we can even go and check the logs. So when you execute, you actually generate logs, right, that can be used by others to check the execution of the contract. So make sure they match. If there's any output, then we better check. And here is the thing that I would want someone to come and help me with, right? So we don't currently check that the gas that is left is exactly what is being said in the test. I believe that when I was implementing this, I did that very quickly. There was a dissonance between the version of the test I was looking at versus the implementation of Hyperledger Besu, which I based myself off. Therefore, some of the gas costs were not matching exactly what was in the test. So that's something that we would want to go back to fix, make sure it's in lockstep with the tests and all that. Finally, we stop the VM. So let's go play, right? Going to run all those tests. The first thing it's going to do here is build the project again. This is happening out of band. This is to run Gradle, and here we go, off to the races. So right now we're posting all sorts of all the logs of what's going on. Here we have something called loop null. There's a couple of tests, a part of this, which are kind of more performance-centric, try to exercise kind of the EVM and its ability to execute. We're not trying yet to optimize for those. I think it would be a little nutty if we try to do that, but I can show you one spot where we could do better for sure. And you can see, right, these are kind of the end of the execution where we're trying really hard to make the EVM hurt. So now we're doing 2 million execution. That does not really happen in the wild. Nobody has that much gas. So while this executes, I can actually show you that. So part of the EVM functionality, which is kind of fun, is to be able to do jumps, right? So you can jump inside the EVM, granted that you have, I'm just going to go to the end again, show you how badly we're doing. We're not doing bad at all, right? So everything here executes extremely quickly, and most of it is reading a JSON file, making sure everything makes sense, and sending that into the virtual machine that we are recreating every time. Every time we're allocating quite a bit of memory for each and every one of them, and we're making sure not to reuse it across executions. So it takes a little bit. But those tests at the end, the reason they can take so long is because in the EVM, you can play with jumps. And for that, think of them as go-tos, right? So there are sources where it says go to that destination, and there are jump destinations. So before you start the execution, what you would want to do is to know all the jump destinations that are available so you can jump safely to them. Some of those jump instructions can actually be conditional to something in the stack. So, saying is whatever is in the stack making sense for the execution. So let me find this again. How many jump destinations? I forget, I'm getting old. Oh, here we go. So here we get the code, and we're going to go over each of the instructions, and we're going to say if the current opcode is 0x5b, then that means it's the destination. If the current opcode is between 60 and 80, that means that it's a push code, so we don't need to care about. No, it's I don't remember. The current opcode, if so we compute all valid destinations here. If the destination that is computed is valid, then if it's not valid, then return an error right away. Otherwise, set a new code position for this result. Right. So, yes. The only issue of those is that we wanted to make sure that we don't fall into the range of push, which would be a problem because we would be having the same jump destination. We could have a byte that looks like a jump destination is actually part of the input data. So if you were to try to find all the bytes that are called CO-X5B in your execution, in your code, you would want to filter out anything that looks like it's actually passed in as input data. So that's what's happening here. Okay, there's a ton of work here, right? So first off, there's always some hardening to do around this type of logic. We want to make sure we do a good job. I wouldn't want to obsess over performance much more. I think it's now going to be more of a game of I/O with how you send that back to the chain, how you store this. We also have all the other hard forks to contend with, right? So Berlin here is the only hard fork that's currently implemented. We need to register every one of the other hard forks and then run all the tests against each of those revisions and make sure that all the gas costs match what you would expect. So that's going to take a little bit of time, hopefully not too long. Of course, the ultimate test is you just take mainnet and you sync up and you make sure that every one of the blocks and every one of those transactions can actually compute and check out to what you would expect. So that's going to be a little bit of a trick in the next thing we'll do. But yeah, we need to pop that into the validator for each transactions, depending on where we are. The Ethereum Virtual Machine itself could be available. Some of the Ethereum clients out there like to make the EVM as a tool that people can call out to do all sorts of checks, like just passing in code and some environment to the execution. What does that look like? How does it execute, right? I don't think we would do that, but I've seen some folks ask me they want to get to the Ethereum Virtual Machine and execute that separately. So we make it available so people can call it from Java. But that's about it, right? So people would be able to just go from there. And that's it for today. Thank you. Please, if you're interested, subscribe to our dev list. It's dev@tuweni.apache.org. Our website has all those coordinates. We welcome anyone, any level. We need documentation. We need eyes on bugs. We need people who operate that code. We need people who can code and want to code in Kotlin or even in Java, dig down in the stack. We are doing some great progress on this, but it's going to take a village. So thank you for tuning in and your attention, and please feel free to bring any comments, any suggestions, corrections to these YouTube comments or to our mailing list. Bye.